All right, everyone, welcome back for our afternoon star-studded. First talk, Carlos Simpson just arrived, going to tell us about secondary deformation classes.
Okay, thank you very much. Thank you very much for the invitation. It's a great honor to speak before Nigel's second lecture. Yeah, so what I'd like to talk about is going to be a little bit formal, not really too much analysis, or really no analysis probably. But I hope this will at least give an example of something kind of really inspired by the idea of a Higgs field. So, okay, so suppose the context here is suppose we have a fibration. And of course, we could just say this paragraph over the base S itself, but we'll really be thinking about the idea of having a subspace of S with the property that on the subspace, at least, the monodromy action of the pi1 of the base is trivial on the cohomological or homotopical invariants, namely the cohomology group, let's say, of the fiber. Then in that case, there's still some structure to the fibration, some topological structure to the fibration. And it's given by some kind of higher cohomology classes. And to get some idea of how this might work is, suppose we take a relative Postnikov tower. So in other words, over each point of S prime, we take a Postnikov tower of the fiber. We're gonna mostly here pretty much always be assuming that the fibration is relatively one connected. So there's no fundamental group on the fiber, of course. That's obviously a future question that would obviously be interesting. But for now, we're just going to be looking at rational homotopy theory in the simply connected case of each of the fibers. Okay, so we can take a Postnikov tower, and then this is given by a sequence of vibrations. When I say quotient, I mean the base of a vibration. And so we have the next step from xk prime. The next step of the Postnikov tower is a vibration over xk. The fiber is, let's say, a k of an abelian group and in degree k plus 1. And under these hypotheses that relatively one connected and the idea that the S prime, pi1 of S prime acts trivially on the homotopy groups, the A, k plus 1, those are the relative homotopy groups of the fiber. So this is going to be a constant local system over S and then pulled back to X prime, okay. And so, well, just sort of the basic philosophy here is that we should think of the cohomological invariants that determine these fibrations as being some kind of secondary or higher monodromy classes of X prime over S prime. And we're going to specialize to the case where S prime is a torus, or real torus, let's say. And so its fundamental group is abelian. Not all that interesting, but still. But we're asking that action to be trivial anyway. On the other hand, it has a pretty big space of cohomology, the exterior algebra of the fundamental group, and dual. Let's say. So it's pretty big, but also understandable. So we have some chance, at least, of being able to calculate in some cases some of these secondary invariants. And now the main viewpoint I'd like to say today is that this picture is going to extend to the case where S has some kind of stacky structure, and S prime is a substack of the form Ka1 for an abelian group sheaf A. So we'll see. I hope if you don't see what that means right now, I hope by the end of the talk you'll have some idea of what that means. Now, two particular cases of this arise in algebraic geometry. The first one is something I did quite a while ago, really. The second one is the thing I'm the topic of today, so to speak. The first case is suppose S is the Dolbeault stack of a smooth variety. Then every point has an abelian group gerb, which is really the source for the Higgs field. I mean, the Higgs field may be viewed as an action of this abelian group gerb on something. The second case, and so that, that fits therefore into this situation. The second case, suppose we take a Dram stack, but with logarithmic singularities along a simple normal crossings divisor D. Then there's some residues there. And these are actions of abelian group. So, if we suppose we have a logarithmic connection, let's say, then the logarithmic connection is going to have a residue, which is the action of a vector space on the fiber over one of the points in the stratification of D. We can view the action of the residue, again, as coming from Ka1 stacks contained inside the algebraic Dram stack, the logarithmic algebraic Dram stack, where A is going to, let's say, be a formally completed commutative group scheme. Now, what we'd like to talk about today is secondary classes for these types of substacks. And the idea is that that's going to be some kind of viewpoint on some kind of stacky aspect of the relationship between Higgs fields and transport. Of course, the theory of Higgs bundles says that when you have a Higgs bundle, then you can get a connection, and that gives some kind of relationship between a Higgs field and a transport operator. Yeah. We'll see that coming up. The next. Sorry. Before that, we'll just do the topological picture, but which I already said at the start, actually. Okay, so just to go back, suppose we have a torus. Let's just replace S by S prime. Suppose we have a torus, and suppose we have a smooth fibration, and we're making this a hypothesis that the fundamental group, which is the Z to the K, acts trivially on. We'll make the hypothesis that this action is trivial, but in any case, it acts. And then I just restated what I said before. The Postenkopf tower for the fiber has a structure involving successive cohomology classes. And the point here is that these classes, why are those classes going to be some kind of secondary invariants? Because they're going to have Leray components, which are higher cohomology classes on the base, with coefficients in cohomology classes on the fiber. Okay. And so let's consider, let's compare. So I mean, the basic idea here is that we're talking about obstruction theory to try to decide whether the fibration is trivial or not. Okay. So if the fundamental group acts trivially on the cohomology of groups of the fiber, you might say, okay, it looks to me like the fibration is probably going to be trivial. Okay. Now, suppose it was trivial. That means then suppose X was a product of the form XS cross S. Then we have the Kuhn formula, which expresses the cohomology of X of the total space as a tensor product. And the Kuhn formula is going to be compatible with cup product. What's in rational homology, at least. So suppose we have a class in the H2 of the fiber, for example. This is the example we'll be looking at. Suppose we have a class in H2 of the fiber whose cup product is equal to, with itself equals 0 at H4. And then let's lift it to a class in H2 of the total space. Make some hypotheses that say we can do that. And in the case of the Kuhn formula, that's class. I mean, suppose we choose the lifting here just as the component of the Kuhn component. You write that down here. Okay, so if we take the Kuhn component, if we just take our class here, okay, then we cup it with itself, we're going to have a class inside C tensor H4 of XS. Okay. Right, the Kuhn formula for H4 of X has a bunch of components, one of which is just H4 of XS. So if eta cup eta equals 0 on the fiber, then it's also going to be equal 0 in the total space. Okay. However, in a general, fibration might have a trivial fundamental group action, but might not be a trivial fibration. And so in the example that we'll be talking about later, suppose H1, I mean, suppose the fibers are algebraic surfaces, right? So if it's simply connected, then H3 is also 0. Suppose we have a base point section, then a class in H2 of the fiber lifts to a unique class in H2 of the total space. which vanishes on the base point section. When you take the Leray form, when you look at the cup product eta cup eta with itself inside the Leray spectral sequence, the term which goes to H0, it's down here, right? In the general case, this has a quotient which is H0 of S, H4 of X, S. Right? So if we take a class going to eta inside here, if eta cup eta equals 0 here, that doesn't mean it's necessarily equal to 0 here, right? Because in the Leray spectral sequence, the abutment of the Leray spectral sequence, it's the graded of the filtration. So it means that the class can project down to a lower degree class. In fact, with the H1s being 0, the lower class is going to be H2 of S with coefficients in H2 of the fiber. Right, so this is the secondary class I'm talking about, basically. Basically, you take something whose cup product with itself equals 0, H4 on the fiber, but then you take its cup product with itself on the total space, that projects down to a lower element of the Leray spectral sequence, and you get a class inside here. Okay. That's one way of detecting having a vibration that's not trivial. Okay, so this is going to be, this is an explicit example. It's the example that I was able to calculate for the Dolbeau case. We'll also see how it has a sort of a non-abelian cohomology interpretation that we'll see in a minute. This is obviously a very restrictive example of the discussion. You can have any kind of classes and any kind of cohomology operations and so on. Okay, so now let's go to the case of the Durham formal groupoid. This is, I think, your first question. Okay, so now suppose we're given a smooth projective morphism of smooth complex varieties. Then let's recall that the Durham formal groupoid is the groupoid object in the category of formal schemes. So you have to parse that sentence a little bit. So we take the category of schemes, but actually, rather than schemes, we want to talk about formal schemes, as we'll see shortly here. Right there, in fact. We want the formal completion. And we want to make a category, but in fact, it's a groupoid. We want to make a category object inside that category. So it's going to have an object and a morphism object that a bunch of maps, source, target, identity, multiplication, and so on. It's just a category internal to that category. It's a category internal to formal schemes, okay? And so let's take the case where the object is S, and the morphism object is something which is a subsheaf of the S cross S, where the first S is the source and the second S is the target map. It's a subsheaf of S cross S, which is the formal completion of the diagonal. Right? So that's not a sub-scheme, but it's a subformal scheme, and we can think of that as the subsheaf in terms of representable sheaves on the category of schemes. Okay. Now let me draw the picture. I'll maybe draw it a little farther over there. So the picture here is that we think of the elements of F Durham as being the links gluing together infinitesimally nearby points of S. So pictures, we have S here. We've got a bunch of points inside S. This is just a picture. This is just a philosophy, okay? But think of S as having a bunch of points. Now we say, okay, but those points are different, so they kind of flop around and do whatever they want, and that's algebraic geometry. If we want to do differential geometry where we want to make a topological space out of that, we need to glue them together. So just think of gluing together all the nearby formal points, basically. All the formally nearby points, okay? So if we take all the points of our space and then just glue them together, then we get the topological space that you get by having that space. Now let's try to draw the morphism object of this. So we want to make this into a category. So, you know, like if this gets glued to that guy and this gets glued to that guy, and then the composition of those two maps is going to be going from here to here, and so on. But the statement was we glued together infinitesimally nearby points. So, like, what would happen if we wanted to just glue together all the points of S? We wanted to glue together all the points of S. That just means we make one morphism between every pair of points. That would just be S cross S. You only want to glue together the infinitesimally nearby points of S. We take all the pairs of points which are infinitesimally close. That's the formal completion of the diagonal. This is going to be. And so that has the structure of formal groupoid. Maybe I should say, I learned about this in Berthelot's book about crystalline cohomology, because what happened was Grothendieck and Grothendieck's thing of these exposés sur la cohomologie de schéma. Grothendieck invented the crystalline site and so on as a way of transforming this picture into the p-adic or characteristic P picture between the two. So all of the books about crystalline cohomology and so on from the 1960s, 1970s, they were all talking about the divided powers and everything. But if you just like read those books and say, oh, I don't care about characteristic P prime numbers and stuff like that, I just want to understand what's going on, then you just like remove everything having to do with divided powers from those books. And that's what you get back out from is this definition, basically. Okay, and this actually represents a stack, and the stack has a kind of somewhat accidentally has a simplified expression, which is just, it's not even a stack, it's actually a sheaf of sets, which is defined by its value on a scheme Y is the maps from Y reduced into S, okay? Basically, because if you have a scheme, if you have a non-reduced scheme and you want to look at maps into the stack, it means you can take since S is smooth, you can locally choose a lifting as to a map into S. But if you have two different points of Y, which are the same on Y reduced, it means that the difference between those 2 points goes into the formal completion of the diagonal. The pair consisting of those 2 points goes into the formal completion. So that gives you kind of a handy expression for this stack represented by this. I mean, in principle, a formal groupoid is going to represent a stack of groupoids. In this case, from this expression, it turns out that's because that's a subsheaf of S cross S. This is just a sheaf of sets. And then there's another way of calculating with this also, which is called Lie-Reinhardt algebras or Lie algebroids. In this case, the Lie algebroid structure on the tangent bundle is just kind of like the obvious one that everybody knows, which is Lie bracket of tangent vectors. Okay. But there's a general theory of Lie-Reinhardt algebras, which are going to correspond to formal groupoids and so on. And this basic example is the one that corresponds to the Dram formal groupoid. And now we have a map of sheaves from S into S Dram. Because the S Dram, we've like added extra morphisms. So if you just forget about those extra morphisms, then that's S. And another way of thinking of the morphism object, it's the fiber product S cross S with itself over S Dram. Okay, now if we go back to our case of a vibration, we can do the same construction on X. So we get X Dram, we have a map from X Dram into S Dram. And then we might want to pull back to S, right? Because we might want to say, okay, let's actually look at algebraic geometry objects over S. The pullback, which is just the fiber product of these. When I say stacks, we're talking about the world of stacks, let's say over affine, maybe finite type probably scheme with, let's say, something like Détal topology. Okay, and the pullback is going to be something which we could call the relative Dram stack. And that's a stack over S itself, not S Dram, whose fiber on a point is the Dram stack of the fiber. Okay? So that tells you how the Dram stacks fit together in a nice way. And it sort of gives you the descent of it gives you the way that spaces are glued together. I mean, in topology, when you have a fibration, you get monodromy and so on. In this picture, It just says that if you have right in X gram, all these points are all the points of the nearby, between two nearby fibers. Those are just by definition glued together. So we're just talking about the transport. So the fact that you have this thing here, this X duram over S, descends to a stack on S duram, that tells you that's the parallel transport in the fiber up to homotopy. Okay, now let's just review what this tells us for bundles on S. A bundle on S duram is the same thing as a bundle over S together with a flat connection. That's really the thing which they said in these books about crystal and cohomology. Right, in general, a crystal is going to be a bundle over the formal category corresponding with that has divided powers in it. But for us, we're in characteristic zero, so a bundle over S duram is just the same thing as a bundle over S together with a flat connection. Flat connection is the thing that tells you how to identify fibers along these little, right? If we have a bundle over the stack, that means that we have fibers over the points, but we have identifications between the nearby points. That's exactly a connection. The fact that, there's at some point, they say this, Grothendieck says this, that's called a stratification, I think. Not the same as what we call a stratification. You could, instead of looking at the full formal cohesion, you could just look at the first infinitesimal neighborhood of the diagonal. That would just be a connection, but not necessarily a flat connection. But it's not a groupoid because it doesn't have composition. Okay. Now, we can take this X duram over S mapping to S, and the relative cohomology, let's say, or homotopy, even invariance, are the usual duram cohomology and, let's say, usual duram homotopy type of X over S. And since these descend to things over on X duram mapping to S duram, this encapsulates directly what's known as the Gauss-Monine connection for the duram topological or homotopical invariance of X over S. And this is like a really quick and categorical way of defining the Gauss-Monine connection on rational homotopy types that was first investigated explicitly by Navarro now. Quite some time ago. Okay, now, so that's the discussion of the duram case, which is kind of just a warm-up for what we're going to do now. Now let's turn to the Higgs picture. Okay, the Higgs picture, there's a Higgs picture corresponding to the above discussion. We can just take this thing and do a deformation to the normal cone along the diagonal. So we can just kind of tilt this thing and go like that. What that does in this picture is it tilts all these loops. It tilts all these little links so that now instead of being links to nearby points, now they're loops at the points. So we've gone back to algebraic geometry, right? All the different points, they're all different. The different points are all different, but each one has a little loop at it. So now rather than being a subsheaf of S cross S, now the F, we'll call this F Dolbeau. Now this F Dolbeau thing is really something that maps to S cross S or X cross S, X. Okay, and so it represents really a stack. And in terms of Lie algebroids, these are, again, you might say trivial, but trivial in a different way. These are Lie algebroids using the tangent sheaves of X or S, but with trivial Lie algebroid structure. So it acts trivial on the functions and there's no bracket, it's just completely zero. So this is the formal groupoid whose morphism object is the completion of the tangent bundle lying over the diagonal, right? So it's no longer injecting into X cross X. And this is the picture that we drew over there. So now suppose we're given a trivialization of the tangent bundle, just locally to write down what's happening. Then the stack looks locally of the form S cross a K cross an Eilenberg-MacLane stack in degree 1 of a K hat. Here, I mean the formal completion of the affine space at the origin. We could write this formula in the following way. I think if I wrote this, you wouldn't necessarily understand what it means, but once we've written the local case, we can understand that this notation just means do that locally over all the points. Okay, now, in the same way that a connection on S duram is the same thing as, a bundle on S duram is the same thing as a vector bundle with connection. A bundle on S Dolbeau is a sheaf on S, is a locally free sheaf on S together with a Higgs field, which is to say the action of these, of the Lie algebroid, or the action of these little loops, right? Here, if you want to have a bundle, you should have a vector space plus an action of the loop on the vector space. Basically, sheaves over a K A1, those are vector spaces with an action of the group A. Here, A is it's a group, but it's a sheaf of groups over the big site and so on. Now, suppose we have a smooth projective morphism. Then we can again form the relative version. I didn't write this down, but this is again the fiber product. We have X Dolbeau over S mapping to S, and the direct image of the structure sheaf being the structure sheaf with its action of the bundle. This is just the Dolbeau cohomology of X over S, which is the RIF lower star of the direct sum of omega J X over S. And remember that this is also the GER of the Hodge filtration on the Duram cohomology, which is direct sum of HQ of omega P. And that's relative to S, okay? So these are bundles over S. Well, let's not. You need to do a little bit of work, or a lot, maybe. You need to do some work to define what these homotopy types are, but you can define the Dolbeau homotopy type for the categorically inclined. It means you define it as the representing object for the functor of non-abelian cohomology with coefficients in certain types of stacks, which are the schematic homotopy types, basically. In the case of relatively one-connected, then that's what that's a way of saying rational homotopy theory, which is that the functor of non-abelian cohomology is actually representable, and it's representable by the rational homotopy type tensor with C. And you can do the same thing for the Dolbeau thing. So you can define the same functor and, yep. Okay. So then we get actions of the formally completed tangent bundle. In fact, since this is the formal completion of a smooth group scheme, you'll actually get an infinitesimal action of the tangent sheaf itself. That's the Higgs field. Okay, now the action that you get on the Dolbeau cohomology is a Higgs field on the Dolbeau cohomology. That's what's known as the Kadir-Spencer map on the associated gradient of the Hodge filtration. Go back a step. Remember, the Kadir-Spencer map jumps by 1 in the Hodge filtration. But now suppose that these Higgs fields are 0. So suppose that the classical action of the tangent space of S is trivial on the cohomology. Then the point of this first part of the discussion is we got a secondary Kadir-Spencer Higgs field that expresses the homotopy coherence relations of the action of the tangent space on the homotopy type itself, on the Dolbeau homotopy type. So let's go back to our example of classes in H2 whose cut product equals 0. We can view those as corresponding to maps to the schematic two-sphere, if you like that type of thing. The schematic two-sphere is something, remember the two-sphere in rational homotopy has 2 homotopy groups. It's pi 2 and pi 3. Right? Pi 2 is Q and pi 3 is Q. And the structure of that is given by a class in H4 of KQ2 with coefficients in Q. And that H4 is equal to Q. So the structure, that's the Whitehead product. The structural cohomology class to define the two-sphere is a non-zero map from wedge 2 of Q to the other Q. So you can just sort of say the same thing, the same words in schematic homotopy types, where GA, I wrote this as GA to me, not all that confusing, hopefully, but the sheaf O is the same as the sheaf representable by the additive group scheme GA, or it's the affine line. And the H4 of KGA2, with coefficients in GA itself or O, is actually equal to O. So that was done by Larry Breen in the early 1970s, I think, which we now call the Breen calculations. He calculated the cohomology groups of all these types of Eilenberg-MacLane stacks. Before we even knew what stacks were, right? Or at least, maybe, I think Larry Breen actually knew what stacks were, but at least certainly on an intuitive level. Anyway, he anyway calculated the structural things you need to know to calculate with these schematic homotopy types. And the fact that it's the same calculation as the Q calculation in rational homotopy theory tells you that you can do the schematization. Okay, so now suppose we have a fibration, then we can form the 3 stack, I guess. This is 3 truncated, so it's already a 3 stack. We can form the 3 stack of the relative Hom from the Dolbeau stack into this schematic homotopy type over S. Okay. The fiber over a point is basically the same thing as the cohomology class in the fiber whose cut product with itself is 0, right? A map in rational homotopy theory, a map from a space into the two-sphere is given by the H2 class, which is the pullback of the tautological class, and it has to satisfy the condition that cup with itself is 0. So now you know how to calculate some non-abelian cohomology with higher stack coefficients, right? Maps to the stack S2 are just cohomology classes whose cut product with themselves equals 0. Then we can, as we said before, we can look at the secondary class, which is the value of eta cup eta, which is going a step down in the Leray filtration. So suppose again that the fibers have H1 equals H3 equals 0, then we're going to get back to a degree 2 class on the base with coefficients in H2 of the fiber. And I was able to calculate an explicit example. It was not so easy in my memory. But maybe it wasn't done in a very good calculating way either. So for the example, we take a smooth projective surface with H20 different from 0. We're going to call that alternatively Z or S, S if it's the base and Z if it's the fiber. Then we let X be the blow-up of Z cross S, which is S cross S, along the diagonal. So that means that X is the family of things that you get by taking different points of the surface and blowing them up. Okay? The point moves around. Now, as the point moves around, the kind of obviously the action on any kind of cohomology or homotopy groups of the fiber, there's no monodromy action. I mean, the surface is simply connected, let's say. However, if we choose an appropriately chosen class, which is you combine the exceptional divisor and a hyperplane class, which over a local patch in S is not supposed to meet the diagonal. And if we choose M and N correctly, which might have to be complex numbers, then we can get eta cup eta equals 0. Okay. So we get a map to the schematic two-sphere. Then you can prove that the secondary class is a map from wedge 2 of the tangent bundle of the base. Right. So remember what we're doing here. We're taking X Dolbeau mapping to S Dolbeau. Then we're looking at just a single point. So we're looking at K of T S 1. Right. A single point is just a single formal loop. Okay. We form the fiber product. Then the relative Dolbeau homotopy type of this fiber product over this space is going to be the homotopy type of the fiber product. I mean, this has the base point, which is S. It's going to be the homotopy type, Dolbeau homotopy type of XS, together with the action of the higher homotopy coherent action of tangent space. Okay? So it means that our secondary class, for our secondary class, we're looking at this guy here as S prime. Okay, that's why I said S prime at the start. So the secondary class is going to be in H2 of T of K with coefficients in H2 of X. Okay. The calculation was that the secondary class turns out to be a map that it goes into H2, the coherent cohomology. This is one of the components of the Dolbeau cohomology. And it's Poincare dual to the evaluation map of two forms. Okay. And so it's non-zero. So by our hypothesis, there are non-zero two forms. So this at least gives at least one example where the secondary class is non-zero. Also, maybe somewhat interesting, although I was never able to see any development of the speculation, but this is the same example. The hypothesis here is the same as these examples where the Chow group of zero cycles on a surface can be sort of really big. So it seems likely that there's some relationship there, but I was never able to see exactly precisely what it was going to be. But anyway. Then in kind of more generality, we looked at a notion of variation of non-abelian mixed Hodge structure. And these secondary Kader-Spencer Higgs fields are going to be the variational data for the Dolbeau realization of those things. We had a lot of trouble understanding the weight and purity properties, came up with some kind of possible answer to that in our preprint. But again, that's not very definitive. Okay, so now let's turn to the second picture. So that was the end of the first picture of my 2 bullet points, okay. Let's turn to the second picture. Okay, now the proofs in this part are even more in progress than the proofs in the last part were in progress 20 years ago. The proofs in this part are currently in progress still. A long-range goal fitting with the Malinka project, which Nigel knows about, would be to go all the way to a formalized proof level, a computer formalized proof level for this type of thing. You can kind of imagine in your mind at least the type of problems that that's going to generate. So we are kind of trying to chip away a little bit at some of those problems. But anyway, but for here, we're just going to stick to the sort of purely formal discussion. Okay, so let me just make a couple of observations. I should probably do these rather quickly, so let me kind of flip through these slides more quickly. These are just basic observations that everybody knows, supposedly. So suppose we have a disk, and the divisor is 0, is just the origin. If we have a vector bundle with logarithmic connection, we get an endomorphism. The residue of the logarithmic connection is an endomorphism of the fiber at 0, okay? And suppose we have a nilpotent, suppose the residue is nilpotent, then we can, I mean, you could do this more generally, but the nilpotent thing assumption is a good assumption up here. Then you can create a model logarithmic connection on the sheet just using V0. And you define the connection just by this formula, D plus the nilpotent transformation times dz over z, okay? So we took a general logarithmic connection on the disk. We look at its fiber over 0. We look at its residue. Then that's just a vector space with a nilpotent endomorphism. From that residue, we can build a model for the connection. And there's a unique, the nice thing here is there's a unique isomorphism that respects both this identity on V0 and logarithmic connections. So in a strong sense, the connection on the punctured disk is determined, the logarithmic connection on the punctured disk is determined just by the pair of V0 comma n. Another way you can express this construction is you can we can take n, turn n into a section, a nabla invariant section of the endomorphism. We can take the connection nabla minus n underline. That's going to be a flat connection. And it's going to induce a trivialization, which is the isomorphism. It works the same way in higher dimensions. Let me just not say. this construction was the first step, really, and that's how I learned about it in the nilpotent orbit theorem for variations of Hodge structure. You can the nilpotent orbit theorem says that you unwind the variation of Hodge structure itself using that same construction, basically. Okay, and of course, it's really the basic thing happening in doing these lecture notes on regular singularities. Okay. And from this discussion, immediate consequence of this construction, which is not completely obvious, if you just say that like that, is that logarithmic connections with nilpotent residues satisfy a strictness property, so they form an abelian category. And in fact, you can even say that this V0 is actually a fiber functor for the tensor category of flat bundles on the circle with nilpotent monodromy. See, if you wanted to do a Tanakian thing, that's why the nilpotent hypothesis is good. If we allowed some kind of monodromy eigenvalues, then when we start tensoring, then you're going to get out of the range. So we were talking this morning about the range of angles. So there's this kind of weird point. So right, there's kind of a weird point of the circle, which is the fiber functor, which is the value at the origin of the logarithmic connection. Then we have another observation, which was contained in the archive version of one of our articles with Jaya here, which kind of says something similar, which says that if you have a perfect complex, because if you think about how would you construct a perfect complex, you would take a morphism, but that would be strict, right? But you can actually show that if you have a perfect complex with a logarithmic connection in the sense of descent to the stack S Durham log, with respect to normal and crossing divisor, if the residues act on all the fibers of V nilpotently on all the cohomology spaces of the fibers, then V splits as a direct sum of locally free sheaves. You can't have, if you have a perfect complex, typically when you have a perfect complex, the cohomology dimensions can jump. When the cohomology dimensions jump, it creates pairs of eigenvalues that have to differ by integers. So if you assume that all eigenvalues are 0, then you can't have that jumping phenomenon. Okay, so now we can just describe the logarithmic Durham formal groupoid. It's sort of a deformation. Deformation from the Durham formal groupoid to the Gilboa one over the base over the point. Okay, so we can define it, let's say, by the Lie algebroid. We can take the Lie algebroid of tangent vector fields that are tangent to D. So those are like logarithmic tangent vector fields. And we can take the formal groupoid associated to that Lie algebroid. But you can also write this down in a way similar to this deformation to the normal cone. And this was discussed in a recent preprint by Michael Bars in December, who did lots of non-abelian Hodge stuff with that, also in characteristic P. Anyway, but you can define a logarithmic Durham stack, which has the property, maybe we'll see on the next page or not, that sheaves over the logarithmic Durham stack. Those are vector bundles with logarithmic connection. If we let this bracket thing be the stack, then the fiber product again is the morphism object of the formal groupoid S Durham log D. Now suppose we have a stack. Suppose we have an n stack over this space. So we'll think of T as being the kind of the fiber-wise homotopy, rational homotopy, or schematic homotopy type of our fibration. Suppose that we make the hypothesis that the pullback is a geometric n stack that's relatively one connected. And then the D has a natural stratification by intersections. The Lie algebroid on the strata is going to be an extension of the Durham Lie algebroid of the stratum by some space of residues. And Ri is the space of tangent vector fields that are equal to 0 on Di, not just of course, or write the normal bundle, really. This phrase doesn't seem to make too much sense, but if you think about it, it does make sense. Okay, so our stack, in the case where we have a stack over this logarithmic Durham thing, then we get an action of the residue space, because that's a subspace of the Lie algebroid. Maybe I should draw the picture. Logarithmic Durham picture is kind of between these two pictures. Right, it's at the origin D, we make a loop, but the other points are Durham, right? So this is Durham. I say this is Durham. This is Dolbeau. We connect together nearby points, except along D, we connect the points just to themselves. If D has higher dimensional components, then we do a Durham groupoid along the components of D, but zero in the Dolbeau type of thing in the normal direction. Okay. Then again, we can have these homotopy group sheaves. Well, they're going to be some kind of at least vector sheaves or some type of sheaves of O module over the strata. Also here, I'm kind of changing notation. I think I'm sorry about that. The notation DI became SI because the big, we might want to think of the big stratum also. Then we get into a situation which is very similar to the hierarchy Dyer-Spencer classes that we considered before. Right, so if we have a point in S, the space of residual directions, that's the normal bundle to the stratum, is a commutative unipotent group scheme acting, at least formally, on the homotopy type over that point. There's going to be secondary residue classes, again, for this action. That's the comment I wanted to make here. Then a typical situation where this happens is when we have a semi-stable family. So, why are we doing this now and not, 20 years ago? Well, one reason is that semi-stable reduction theorem for higher dimensional base with higher dimensional fibers was only shown fairly recently, okay, maybe 2018, by Adipasu, Yu and Temkin, following the ideas of Abramovich and Karu. This tells us that general morphisms, given a general morphism, you can make a ramified cover of the base and make birational modifications of the base and the fiber to get to the case where it's semi-stable. So that means that it now makes sense to study the case of semi-stable fibrations as a model for the local topology of general fibrations. I think this is not, when people do minimal model theory and higher dimensional and bidimensional geometry, the type of singularities that they talk about are rather far from being normal crossing singularities. So I think it's still not at all evident how to go from, a log terminal singularity or something like that to an actual semi-stable picture. But at least now we know in principle it's possible. So we can consider having a generically smooth semi-stable morphism. Let's now, from here on, D is the divisor in X, and we'll call P the divisor in S, okay? So these are simple normal crossing divisors. We have a relative formal groupoid, which is the same, defined in the same way as before, which is the logarithmic Durham. I think I didn't think completely about this, but I think I don't see why you couldn't also have a horizontal divisor and take also logarithmic things with respect to a horizontal divisor. I'm not completely sure about what exactly the semi-stable reduction statement says in that case. But that should probably work. And then this is going to have a descent to a formal groupoid over S, the logarithmic Durham stack of S with respect to the divisor P. And we can look again at the schematic homotopy type and so on. Actually, about almost done really, in the sense that to define this, T is the relatively geometric and very presentable stack, which represents the non-abelian cohomology functor of relative to S. So T is universal for maps to that type of n stack. And the main observation is that the residue, again, which is just this complex k-dimensional space, k is the codimension, that's the normal bundle, acts on the homotopy type TS. So as before, it's going to have an action on the homotopy groups, sheaves or whatever. But if those are trivial, then we'll have these higher classes in the same way as before. Then kind of a comment, but maybe I'll skip this quickly. But in principle, you should be able to explain the logarithmic Durham homotopy type of the central fiber by just using the Lie algebraids over the pieces of the stratification that go over the central fiber. You have to understand how to glue those together. Then we also have nearby points. Okay, so if we have a point in the divisor, then we have the link around that point, which is a small torus near to S. Sorry, I should have said this is the small boundary of the k-dimensional polydisk. Okay, so if we take a base point of that torus and it's a nearby point, then in the topological world, we get back to the case that we had at the beginning, which is we have a fibration over a torus. But then we can also, and so we have the secondary invariance in the topological world. And we also schematize to get the schematic homotopy type of the nearby fiber. So now we have the same homotopy type. You can the Durham homotopy type and the Betty homotopy type are equivalent. The schematic homotopy types are the same. So we have the same homotopy type with two different actions, either an action of the residue space or an action of the ZK, which is the fundamental group of the link. And the question is, can we compare these? And the answer is obviously supposed to be yes. Doesn't seem completely easy to understand how to prove that, actually. And so maybe we should make the hypothesis again that we have nilpotent action. This is going to be true for the semi-stable families. In fact, then this is the in progress, the most in progress part here, which is that under this hypothesis, this is part of the in progress. Under this hypothesis, the cohomology sheaves and homotopy sheaves of the homotopy type are locally free. That actually comes from that observation. Suppose, okay, it's polydisk. Then here again, it needs a little bit more work, but I think we can create a model kind of exponentiating basically the action, but it's a higher action of the residue on the homotopy type of the fiber. And then you'd like to say, okay, there's going to be a unique isomorphism compatible with the formal groupoid actions and the identity on T0. The basic sketch of proof of that will be by Postnikov reduction to go one stage at a time in the Postnikov tower and use those observations about the triviality, local triviality of logarithmic connections with nilpotent residues. So a corollary will be that the action of pi1 of the link on TS is going to be the exponential of the action of R0 on T0 via this identification. So the secondary, so up to some normalization, the secondary invariants of T0, which come from the residue of the Durham homotopy type, are going to be the same as the secondary monodromy invariants of the nearby fiber. That should be an A there. Okay. So good, I'm on my last slide, except for the references. Okay, so I just wanted to say a couple of further directions. So I think it will be interesting to use the Hodge filtration to compare these deformation invariants and the limits of the secondary Kadeir-Spencer classes, which is they combine these two pictures. We had the Higgs picture, then we had the logarithmic Durham picture. But the Higgs picture should extend, there should be like a logarithmic Higgs picture extending over the divisor, the base. It would be good to compare those two things. So a typical, let me just mention, there's Hodge theory gives you some topological information about monodromy we can recall. Namely, there's a theorem that says that just if you have a family over a punctured disk, right? a theorem from the theory of variations of pod structure tells you that the maximal length of the chains in the Jordan type of the monodromy transformation is bounded by the maximum length of the chains in the Hodge filtration. Right? If the Hodge filtration of the fiber has, it looks like this. I suppose, you might have a degree 3 cohomology, but maybe the two end pieces happen to be 0. If the cohomology looks like that, then it tells you that there's only the maximum nilpotency of the monodromy transformations is bounded by 1. So you might expect to have that might be a motivation. You might expect to have a similar type of statement here. I'm not sure about that. Also, unfortunately, I'm sorry, but I don't have actual examples. I had an example in the case of the secondary Kadira-Spencer class, but I don't have examples for the secondary residues. So good question is to look for those examples. I think they should exist. I strongly doubt that it would be the case that those happen to always be 0. That doesn't seem reasonable. And of course, we might want to look at that in the case of moduli spaces of Higgs bundles and so on over the base, which is to say, remove this hypothesis of relatively one-connected, that we would be looking at the fundamental groups of the fibers and the moduli spaces of local systems, and those have higher stacks over them also. Okay. So I'm done, but let me just put on the screen some of this is totally not a exhaustive collection of references, just a few references of stuff that they entered in here. Okay.
Are there any questions?
You had this example in the case of Kadira-Spencer secondary classes, where you have a surface and you're blowing up the surface at a moving point. Could you comment on what led you to that example, or is there some significance to this particular example?
You have to look around a little bit to get something where it looks like you'll be able to do the calculation and that it's going to give you something non-zero. And I'm not sure I remember completely, but maybe part of the ingredients were that looking at the Hodge type of what was the class going to have to be if it was going to be non-zero. And if you want to have like surfaces to be as easy as possible. I don't think that's not going to happen on curves, I don't think. Not completely sure, but it might happen in the fundamental group case for semi-stable but not stable connections possibly, but it's not going to happen for higher homotopy type on curves. So you need surfaces at least, let's say simply connected surfaces to be easy. And then just looking at the Hodge type, you kind of see that you're going to have a H20, H02. So that pretty much led to the hypotheses there. And in some way, also why do we blow up a moving point? That's like the easiest way of getting something where you're sure that there's no monodromy on cohomology. That's, you might say, that part of the difficulty in general is that having the monodromy be trivial, it might be that when you go around, you take your class and you move it around, it comes back to a different cycle. That cycle is homologous to the original cycle, right? But what's that homology? That homology might go kind of everywhere. That's kind of what's stopping me from being able to understand the examples in the residue case. So in this case, where you're just blowing up a point and moving the point around, you can't have any possible monodromy because the surface is simply connected.
Other questions? Okay, well,
Yeah, so also if you take the bow stack and look at the mapping stack into some group, you get moduli of Higgs bundles. So I was wondering, like, what is is there some concrete meaning to the secondary class in terms of Higgs bundles, in terms of mapping stacks out of this vibration or something?
Well, I think so. Isn't that what we just said? I'm not sure. The secondary class is given by the restriction to this thing. So it's the mapping stack here. I guess, yeah, I see. we're looking at, instead of looking at the stack itself, we're looking at the relative Hom of X del Beau over S del Beau into some other coefficient stack. In our case, S1, S2. And the non-abelian cohomology construction works relatively. So this guy is going to be relative to S del Beau. This is the relative Hom into this thing. That's going to be something which is relative to S del Beau. So but that's just going to be happening. I mean, you can do the same construction in the fiber here. So this construction is just going to be happening in the fiber here. And I'm guessing that's why I was talking about the Lie algebraic structures and so on. I'm guessing that you can just do the construction on XS, but sort of keep track of the vector space action. You have to keep track of it in a higher homotopy coherent way, basically.
Okay, so there are no more questions. Let's thank Carlos again.
Thank you.